Good afternoon, everyone. Welcome to this webinar. My name is Berend de Bie. I'm a technical advisor at SpiroTech. In my daily work, I get a lot of questions every day about designing and selecting pressure maintenance systems. Today, I want to walk you through a topic that often creates a lot of debate in practice. How do you make sure your system has the right pressure, and how can EN 12828 help with that? There's also a moderator in the chat who can pick up any questions you might have along the way. And if you can't answer something straight away, don't worry, we'll come back to it later. We're nearly starting with the main topic of today, but first I would like to mention that we have a poll open in the chat, which can be found in the bottom right corner of your window. If you have not responded, I kindly ask you to do so. In the meantime, for those of you who may not know us, SpiroTech is a Dutch manufacturing company based in Helmond. It was founded by the Roffesen family back in the mid-20th century. They were the inventors of the SpiroTube, which later became the foundation for solutions that improve system water quality and in turn help to save energy. Today we are active in more than 75 countries with a sister company called Eder in Austria. Let me quickly show you today's agenda. The goal of this session is to get a clear understanding of the different pressures inside a heating or cooling system and how these pressures relate to each other. We'll also look at how we can influence these pressures and how to correctly select a pressure maintenance system. And we'll do this in line with the requirements of EN 12828 Annex D. If you have questions during this webinar, the best way is to post them in the chat function. We'll try to respond to as many as we can right away. And if that's not possible, we'll make sure to come back to your question later. We've closed the poll now, and maybe we can have a look at the results. What I see is that there's quite a spread. So most of you use some kind of system to select pressurization, and some have never done that. So it will be quite interesting, and let's see if we can improve your knowledge of EN 12828 and selecting pressure maintenance systems. Let's start with a chapter on basic hydraulics, and this is where we lay the foundation for today's topic. In a hydraulic system, there are several components that influence both the static and dynamic pressure. The static pressure is mainly determined by the height of the system. The higher the top point, the higher the pressure at the bottom of the system will be. The dynamic pressure is influenced by components such as the pump, valves, piping, the heat source, for example a boiler, and users, so fan coils or radiators. These all cause pressure losses due to flow and resistance. The effect of all these influences becomes clear when we show the system pressure development in a pressure profile, a graph that shows the pressure at different points in the system. This makes it visible where and why the pressure drops or rises, and why the position of a component like the expansion system is so crucial. You could say the height of the system gives us the static pressure, like a water column that's always present. But once the water starts to move to transport energy through the building, every component in contact with the water influences the pressure. That's the dynamic pressure. The pump adds this pressure because it provides head, and all the parts where the water flows through consume this pressure as pressure losses due to internal resistance. These two, the added head and the pressure losses, are in balance because the amount of water flowing adjusts accordingly. This becomes visible when we plot a pressure profile of the system. Let's take a building as an example. On the left side, I'll get my laser pointer, we have a boiler with a pump, and on the right side we have the farthest end user, or the farthest user at the end of the system. And in between we have piping that transports the energy. Now if we would put an expansion system on the suction side of the pump, which is here, the static height that we use to determine the pressure maintenance becomes visible, and it's shown in green. So from the suction side of the pump to the highest point in the system, that's the static height. Now let's see if we can create a pressure profile based on this building, and we'll do it according to EN 12828. Now, for the pressure profile, we use the pressure definitions as described in the norm, so EN 12828, and these are also the same values we apply in our standard selection process. In this graph, the static pressure is shown for the example building. So the example building is here. The x-axis represents the length of pipework, so from 50 meters from the boiler to the farthest user, and 50 meters back to the boiler. So this is where we see the boiler in the graph, number 1, and this is where we see the farthest user, number 6. And the numbers in between correspond to the numbers in this building. So 2, 3, 4, and 5, 2, 3, 4, and 5. Keep in mind, what you see here is only the static pressure. On top of the static pressure, we always add a minimum safety margin to make sure the system remains filled at all times. If required, you have to include an extra factor to prevent evaporation. This pressure is shown as the yellow line in the graph, also known as P0 in EN 12828. On top of P0, we add the water reserve, which equals to 0.3 bar. In the graph, this is shown as the brown line. I'll point it out here. So the brown line is the top one. In the norm, this pressure is called P ini, or initial pressure. Now, once the system is filled to a pressure above P ini, so initial pressure, we switch on the pump. And this is shown as the red line in the graph. So here. The pump adds about 2.3 bar of dynamic pressure. So from this pressure to that pressure, I can't really see which pressures we have. And because of the water flowing through the pipes, there is resistance, of course, which causes pressure loss. In this example, it's 1.8 kPa per meter. The pump head is consumed by this pressure loss throughout the system. The red line shows the total pressure at every point in the supply line. So this pressure is the total pressure at this point in the system. And the highest pressure is also known as the total pressure in the entire system, which is here. On the far right side, so at this point, you also see the load, which is the farthest user, and that has a pressure drop of 0.5 bar in this example. Of course, the water also flows back, so I've added the blue line. This is the return line, and this makes the water flow back to the suction side of the pump. So now you can see the entire pressure profile, which means we can read the pressure at every point in the system. This is what the different pressures look like once the system is filled and started. Of course, the system also requires an expansion system, but we'll go into that later. On the next slides, you'll see an overview of the pressures defined in EN 12828 standard, now made visible in the pressure profile of the system. Minimum allowable pressure P0 is defined as static pressure plus 0.2 bar plus the evaporation pressure. That's the yellow line. This value also corresponds to the gas precharge pressure of an expansion vessel with a fixed precharge when installed on the suction side of the pump. On top of the minimum allowable pressure P0, we add the water reserve. This water reserve is used to keep the system filled when there are small water losses. Together, this gives P ini, or initial pressure, the initial system pressure, or the lowest cold fill pressure. By default, this pressure is set to about 0.5 bar above the static pressure. The cold fill pressure is the pressure at which the system is filled in cold condition, and this pressure is higher than P ini. It is the baseline from which the system starts operating before any temperature increase. Safety valve pressure, so the top line, shown here, is the pressure indicated on the safety valve itself. But keep in mind, everything that sits between the pressure maintenance system and the safety valve has an influence on the pressure setting that should be chosen for the valve. The maximum allowable pressure is the highest pressure the system may reach. It's shown here. but always with a margin below the safety valve setting so that the valve does not open. This ensures the system operates safely without triggering the safety device under normal conditions. The safety valve opening margin is the difference we need to maintain between the maximum allowable pressure and the safety valve pressure. According to EN 12828, this margin is 0.5 bar or 10% of the valve setting, whichever is greater. The working range of the expansion system is the band in which the system can safely operate. It's shown here and there. So it's bounded by the minimum system pressure, which is that line, and the maximum system pressure, which is that line. Below the minimum pressure, the system risks issues like air ingress or partial evaporation, and above the maximum pressure, you risk opening the safety valve. So the expansion system must keep the operating pressure within this range across all conditions, which are cold start, heat up, peak load, and cool down. I've mentioned this one before. The total pressure in the heating system is the highest pressure anywhere in the system, the peak pressure the installation experiences. It's the key reference for component ratings and for keeping enough safety margin below the safety valve setting. The system pressure differential is the amount of pressure the system uses when water is flowing, effectively the pressure drop across the system. It's equal to the differential pressure generated by the pump at its operating point. It's shown here. The relative pressure maintenance point, which is here, is the location in the system where we hold or reference the system pressure. In this example, it's on the suction side of the pump. And this is also where the expansion vessel is installed. Because the vessel fixes the pressure at this point, the discharge side rises by the pump head, while the suction side remains approximately at the vessel pressure, aside from small dynamic effects. In the pressure profile, this point acts as the anchor. So the connection point of the expansion system is really an anchor for the pressure profile. That's the point where the pressure does not change and cannot change. This slide simply shows that the expansion vessel is connected at the pressure maintenance point in the pressure profile here on the pump suction side. And we'll show the importance of this position later in the presentation. All right. We'll now continue with this pressure profile and look at how the connection point of the pressure maintenance system affects the pressure throughout the installation. Changing the connection from the pump suction side to the discharge side or elsewhere changes where the profile is anchored and therefore which parts see higher or lower pressures under operation. In the next slides, we'll compare these setups and highlight what shifts you should expect. We now have an expansion vessel on the suction side of the pump. This setup is called suction side pressure maintenance. Because of the vessel, the zero or reference point of the system sits on the pump suction side, which keeps the pressure here relatively constant during operation, aside from small dynamic effects, of course. The pressure profile is the same as before, but we've added partial load lines, a pressure drop in the pipework due to line resistance of 0.5 kPa per meter instead of 1.8 kPa per meter at full load. So we're showing the partial load profile when the system load ramps down. Because the expansion vessel sets the zero a reference point on the suction side, so here, the pressure cannot change at this point. And therefore, when the pump reduces head at partial load, the discharge pressure must drop accordingly. So there's no change at this point, but if the pump changes the head, so changes this pressure differential, the discharge pressure will come down. So it will go from this point to that point. Now, if the pump does that with suction side pressure maintenance, the system remains stable with positive pressure throughout the entire installation. And you can see that because all the lines are above the atmospheric line, which is the baseline here, the x-axis. Some extra context. water is practically incompressible, and under steady operation, the mass flow rate entering via the supply equals the mass flow rate leaving via the return. So the same amount of water is coming back from the system through the pump as it is leaving from the pump. So there is no net accumulation of water in the circuit and no exchange with the expansion vessel in this state. Nothing that would change the set pressure. The pressure maintenance simply holds the reference point. So there's no water flowing into the vessel or out of the vessel. The pressure stays the same. There's no water flowing into the vessel or out of the vessel. That means the pressure can't change. Okay, let's make some changes. The same system as before, but the expansion vessel is now connected to the pump's discharge side, so at the top point here. This is called discharge side pressure maintenance. That means the pressure at the pump discharge is held constant, aside from the same small dynamic effects, of course. Now, important is that in this setup, the vessel pre-charge and the initial fill pressure, so P-ini, are different from the suction side configuration. They need to be quite a bit higher because this pressure needs to be maintained and not that pressure. At full load, the pressure profile looks the same with suction side pressure maintenance if the vessel is set up correctly. The difference appears at partial load. We'll see that next. Now, with the vessel on the pump discharge side, the discharge pressure is held constant, so this pressure is constant. That means when the pump reduces speed or reduces head, the discharge pressure stays the same. So this pressure stays the same, while the suction pressure rises. So the pump differential drops, and that means something has to happen. But if the pump discharge can't change, the suction will change. So the suction pressure will go up. So with discharge side pressure maintenance, the system pressure tends to sit at a consistently higher level across the operating states, which is rarely necessary for standard heating or cooling loops. However, there are use cases where this is desirable. A key example is solar thermal collectors. When the circulation pump stops, keeping a high pressure helps to avoid evaporation or boiling and steam formation in the collector circuit. But this is hardly ever necessary in standard heating or cooling systems. Now, what happens with discharge side pressure maintenance if the vessel pre-charge or system pressure isn't checked regularly? Over time, the gas pre-charge can drop, for example, by diffusion. This occurs faster when the pressure is high. So when the vessel is connected at the discharge side of the pump at high pressure, this happens more quickly. As a result, the pressure at the reference point, so this pressure, the pump discharge, will fall. It will drop. So the discharge pressure will end up much lower than before. At partial load, this is not imminently critical because the dynamic differential is smaller. The suction pressure therefore does not drop very far. You can see that it doesn't drop very far. It stays above atmospheric. There's no real issue. But at full load, the pump produces a larger differential. So the suction pressure will drop further, and that's where the issues can start. Here you see the effect when pre-charge or system pressure has fallen and there is real heat demand at full load. So at full load, the pump creates its maximum differential. So the maximum differential can be seen here. If the reference level has dropped, loss of pre-charge or system pressure, the entire pressure profile will shift downwards. Discharge pressure is lower than intended. Suction pressure drops even further and potentially approaching atmospheric pressure at high points in the circuit. This increases the risk of air ingress, local evaporation and cavitation in the pump suction, leading to noise instability and reliability issues. At full load with discharge side pressure maintenance, the suction pressure can drop below atmospheric, causing air to be drawn in to the system. In other words, when the demand is high, things go wrong. With this connection, it's even more critical to monitor both the system pressure and the vessel pre-charge closely. That's why suction side pressure maintenance is strongly preferred. It keeps the reference on the suction side, helping to avoid subatmospheric conditions. And these conditions can be seen in this screenshot. So you can see the pressure has dropped below zero, which means air is being drawn in. Air ingress harms water quality. So if you put oxygen into your system, you'll get corrosion, which reduces efficiency and increases maintenance costs and energy consumption. When air is drawn in, oxygen enters the circuit. Oxygen drives corrosion of steel components, so radiators, pipework and heat exchangers, and forms magnetite, and you'll also see gas pockets. So consequences of this are worse water quality, reduced heat transfer, clogging of emitters, valves, strainers, pump wear and higher maintenance costs. But the root cause is here suction side pressure below atmospheric, as shown on a previous slide. So if the pressurization is wrong, this can happen. So that's why it's really important to make sure you get it right. Now, to bring the system back into the right water quality range, combine the correct application of a pressure maintenance system with a water analysis to find out which corrective measures need to be taken. This analysis can be carried out by the SpiroTech laboratory. To remove accumulated air and dirt, use air and dirt separators. This stabilizes the circuit, protects components and recovers efficiency. We're now moving into Chapter 3, SpiroExpand Selection. In this section, we'll translate the pressure profile and the EN 12828 requirements into a practical selection. Now that we've looked at the building and its pressure profile, it's time to see how to select a pressure maintenance system and which inputs you'll need. We'll group these inputs into three buckets, so pressure, volumes and temperatures. These parameters are also defined and used in the norm. In this slide, you'll see an overview of the pressure levels that must either be calculated or taken from the design in order to size or select the pressure maintenance system. These levels, so P static, static pressure, zero pressure, initial pressure, etc., are defined in EN 12828, and we've seen these before, in the pressure profiles. Now, a quick check. For a correct selection, we need a few volumes, which are sometimes really hard to get, and they all must be calculated from system values. First, the total water content. That's a difficult one, and we often see issues with getting the total water content of the system because it's just not known. From that value and the temperatures or densities, we get the thermal expansion volume. On top of that, we add a water reserve for top-ups, so these are shown here, and bleeding. Together, these define the minimum usable vessel volume, which leads to the nominal vessel size in the next steps. As said in the previous slides, we also need the expected temperature range. Think of the lowest system temperature, often the cold fill, the return temperature, the maximum operating temperature, and the safety limiter set temperature. These values drive how much the fluid expands and gives the expansion coefficient E, which in turn gives the expansion volume we must provide. This slide ties the key inputs back to the system layout, so you'll see where to read or derive them. For both heating and cooling, you can locate the static height, which is here, P0, I think it's here, P ini, so initial pressure, and end pressure or final pressure. The safety valve setting, PSV, and the relevant temperatures, the minimum, the maximum, safety, etc. Beside these, you'll also need the total system volume and the fluid medium. These are used to calculate the expansion volume and the required vessel size. A short comparison between fixed gas systems, fixed gas vessels, and spill type or pumped expansion system. In a fixed gas vessel, only part of the nominal volume is usable because the gas cushion compresses between P0 and P fin. So you can use only as a maximum 50% of the vessel size, but that's really depending on the pressures the system is operating in between. In a pumped or spill type vessel, the pressure in the vessel is atmospheric or pressureless. So almost the full tank volume is usable. You don't need to compress any gas. Bottom line, for the same expansion volume, the pump tank can be significantly smaller, and that when the pressures go high, this really becomes very significant. All right, a quick pulse check. A poll will pop up in the chat, and the question is, are you still keeping up? Please select the option that fits you best. There's no judgment, it's just to see where we are. I'll give you a moment to vote. Now, while you're answering, a short recap. We've mapped out what you need for a correct selection, so pressures, volumes, including the expansion volume, and temperatures. We also touched briefly on fixed gas versus pumped spill type systems. With pumped, the tank is essentially pressureless, so you can use almost the full tank volume, which often means a smaller vessel and therefore less required floor space. And yes, you can crunch all of these by hand, all these numbers, all these calculations. You can follow EN 12828 and keep track of set points, watch the working range. It's doable, but it's also a lot of math and a great way to discover the one cell in your spreadsheet that decided to misbehave. However, the good news is there's also an easier path. In a moment, I'll show you the selection tool. You put in the exact inputs we've just discussed and it calculates the expansion volume, the key set points and the required vessel size. And of course there's also the control unit for a pump system. Plus it has some safety checks against limits and safety valve. So you get a non-compliant selection very fast. Now let's have a look at the poll results. It's quite interesting. It's starting to get a bit complex for some of you, which is perfect because the tool will make it much clearer. All right, let's open the selection tool and walk through one or two examples together. I'll just need to log into my laptop. Just a second. Oh. No. I'll put in some inputs and you'll see how it builds a solid defensible selection. I would like to first take the example we had and go through that. What you see in the selection tool, if you go to the main page, is an entry page where you can choose what you want to do. A total solution for a complete system overview, the basics for a system, so a pressurization system, dirt separation, deaeration, and water treatment. But I would like to just enter into the Spiro Expand part of the tool, which gives a selection of the expansion system, so the pressure maintenance system. Right, what we need to fill out are the details of our system. First, in our case, we have a heating system, for example, and we'll add some temperatures because it was a heating system. We add the temperatures because that has an influence on how much expansion volume you can expect. So the expansion factor E, flow temperature and return temperature. I'm entering static height in our system. It was 5 meters. Safety valve pressure. Fine, I'll set it at 3 bar. An operating load, because based on the loads you can do a calculation. I don't know, maybe we have 200 kilowatts. If we don't know the system volume, we'll just calculate the estimated system volume, and that this toggle gives us a selection for a certain factor based on operating load and liters per kilowatt. I don't know, maybe we have underfloor heating, so we'll use that. That gives us a system volume of 3,400 liters. And we just click on System Selection. This will give us an overview of the solutions we have. They can be compared by this star diagram. You just focus on what's important for you. If you think price is important, then you choose the yellow one. If you prefer connectivity, so more information to the building management system, you take the black one, which is the bottom one. I'll first take the fixed gas solution and see what we get. Now for this system, the fixed gas solution is a 230 liter expansion tank. Now the tool will give you a calculation on all the volumes you need to take into account and the values you need to take into account. You get the water reserve of 17 liters, which is 0.5% of the 3,400 liters. Expansion volume, the physical expansion volume, 56 liters, and the total expansion volume. And with this value, the vessel is selected based on the pressures it needs to work between. You select whatever you want, whatever you need for your system. Of course, you want a safety valve, and this is also an interesting part that's really handy because it's a maintenance unit which can be connected between the vessel and the system, and this makes it really easy to check your pre-charge and to check if the vessel is still in working order and if it's okay, because you need to do it at least once a year. So I'll leave those in. I click on download, add a customer name and a project name, and then I download, and you'll get a PDF with everything you've put in, an overview, customer name and project name if you fill them out, your system type, all the data you've put in, and below that you get your selection, whatever you selected, so your solution, the vessel with all the details and the data sheet, some information on how to set up the vessel, and just a list of everything you've selected. Now if you think, well, I'm not sure if this is right, I want something, a slightly different solution, you just click on the blue bar and you go back to the site, to a site where you can choose the other solutions again and make your selection again of what you want. That's how the tool works. Now this is the basic version of the tool. If we go back to pressurization details and we do the selection again, but we want to have more input, or we have a slightly different system or different requirements, we click on expert mode, which is here. This gives you more flexibility on selecting your solution, because it gives you more input on safety, on temperatures, for example, the safety temperature, what medium you're using. We've now had water, but you can also choose glycol, ethylene or propylene glycol with a certain percentage. I'll keep it on water. And for example, if you have a minimum plant temperature that's different from 10 degrees, which is fairly standard, you can fill that out as well. Also with the pressure values, you can add some different values. If you, for example, know that you have an air handling unit or a fan coil or something on the top of your building that requires some additional pressure, so an extra overpressure. And keep in mind that we follow the norm. So the minimum overpressure at the top of the building is 0.2 bar. You can change the working range by sliding these bars. For example, you want to work between, I don't know, 2 and 3 bar. This also slides the safety valve pressure to the correct setting. Now for the system operating load, that is the same, so it's still a certain power, but you also have the option to add additional system volume, and then you can think of buffer vessels, which are quite common nowadays and used quite a lot with heat pumps. So you can add those because they are significantly adding to the system volume. And below additional requirements, you can see a certain room height, insertion opening or door opening, and a maximum vessel size if you know that you only want to use, for example, 500 liter vessel size, so 500 liter vessels in a spill type system. Now if you fill those out, you click on system selection, and again you get the solutions like before, but tailored to your more elaborate needs. This is how we work with the in the selection process. You can use it as well. You can find the link to the tool on our website. Please feel free to use it, And should you have questions on a certain solution, there's an additional button. For example, that's this one, advice or price support. So if you found a solution, but you're not sure you want this, or you have questions regarding the solution, you click on this button, you get a pop-up, you add your name, email address, phone number, postcode and your country. You send it out and we get this information and we'll contact you to help you in your selection. All right, this was what we had regarding the tool. And if you can go back to the main screen now. Ooh, to use the right mouse. Are there any questions that need to be answered? I'm looking at my moderator. Nothing for now. It's all done. It's fantastic. It kind of means that we've explained everything, if there's no real question. And we hope we've given you some interesting insights, and we'd like to thank you for your attention. But please, before you head out, could you please fill out the evaluation form? We've put a link in the chat, and we'll also distribute it by email after this webinar. It takes about a minute and it really helps us improve these webinars. Thank you all for joining us and have a great day.